Yes, my name is Carmen Sanz from the Chemical Engineering Department of the University of Barcelona. And I want to thank the organizing committee for inviting me. This is my first time in the summer school. And they proposed me to talk about photolysis. Okay, and I thought about school. So I'm a teacher at the university, so I prepared a very basic, fundamental talk, at least compared with the previous talks. So I hope it will be okay for you, because I prepared some photochemical fundamentals from the beginning in order to better understand, in general, photochemical reactions. And then I'm going to focus on the main photolysis reactions that they are important. Maybe not that important in water treatment, but they are quite important in the environment because of the pollutants we are releasing in the environment. We will talk about that. So I will talk about direct photolysis and indirect photolysis, a little bit about vacuum UV photolysis of water, and I'll give you some general bibliography, but very specific in photochemistry, where you can, of course, find a lot of much more specific information about this topic. Oh, sorry. Yeah, I told you that it was very fundamental. I will start with the first concept that you already know about radiation. When we are supplying radiation to a media, we are supplying energy. And this energy is going to be used in chemical reactions. So it's important to remember, to review, that radiation, we can consider radiation like a stream of photons that travels in straight line at light velocity, and each photon carries a parcel of energy. Okay, and this parcel of energy is characterized by the frequency or the wavelength of the electromagnetic field. So you already know that the electromagnetic field is very broad, but in photochemistry, the interesting part of the spectrum that is used for photochemical reactors are comprised between visible, that is about 700 nanometers, down to UVC or vacuum UV, about 100 nanometers. And you also know that the higher the wavelength, the lower the energy that is included in these photons. Okay, when we want, sorry. The equation that relates the energy carried by this photon is the Planck equation. You also know about that. And in photochemistry, normally we don't work with photons individually, but we use, in reactions, we use moles. So photons will be part of the reactions, and normally we also use moles of photons as a way of quantifying these reactants. So if we multiply the Planck equation by the number of Avogadro, we get an expression that relates the energy that is carried by a mole of photons, what is also called in photochemistry by an Einstein of photons. Okay, this energy, as I told you, depends on the wavelength, and if we are working between 200 and 700 nanometers, means that the energy we are supplying with every Einstein or mole of photons will be comprised between 600 down to 170 kilojoules per mole. For example, this is a very basic exercise, but okay, I hope it was interesting. If, for example, if we have a 4-watt lamp that emits mainly at 254 nanometers, and we know the radiant power efficiency of this lamp, that is the energy that the lamp, the energy that is transformed into radiation from the energy that is consumed from the lamp. If we get this data, using the Planck equation, we can know the energy that is contained in 1 mole of photons at 254 nanometers. So if we have the total energy that transforms the lamp into photons, and we have the energy of 1 photon, we only need to divide, and then we get the photon flow of this lamp we get the moles of photons that is emitted by the lamp per unit of time. And this is very important because we will see, or you already know, that this affects directly on the performance of the chemical reaction. Okay, so we know the basic from radiation. Next, what happens with this radiation when it reaches the system, the matter that we are irradiating? Basically, they can happen different physical phenomena. The most important ones is part of the radiation can be absorbed, part is reflected, and part can be transmitted. Absorption is very important. We will remember that, because only that the absorption that is able to be absorbed will be used on chemical transformations. So this is very important to take into account in chemistry. So each photon will react just with one molecule. Okay, so it is not so important the radiation that is emitting the lamp, but the radiation that is able to be absorbed by the chemical compound. So absorption is important, and of course you all know this equation, the Bernoulli equation, where you relate absorption of radiation, that is the inverse of, in log phase, of the transmittance of the media, with these three parameters. This is the molar extinction coefficient that is characteristic of each compound, the concentration of the absorbance of the compound, and the path length of the radiation. So, important characteristic of a system that has a compound and absorbs radiation is the absorption coefficient. The absorption coefficient, as we saw, is the product of the molar extinction coefficient and the concentration of these absorbents in the media. So, if the molar extinction coefficient of the compound is high, this means that the system will have a high absorbance. The higher the molar extinction coefficient, the higher the absorbance. And this is promoting at least the probability of chemical changes. If this molar extinction coefficient is not high, we still have concentration. We can increase concentration and then increase the absorbance of the system. If both are important, if both are high, we will have bigger absorption in the system. Another concept that I wanted to review, to remember, is that absorption is an additive property. And in chemical reactions or in nature, normally you don't have only one single compound, but you have a mixture of compounds. So the absorption of the system will be a competence between the compounds in the media, that is, they are able to absorb this, the radiation. So the absorption is an additive, let's say also a competition process. And you already know that if the absorption is bigger than 2, we can say that the transmittance is lower than 100%, so the absorption is total. Here I put some tables where you can find, on the bibliography, where you can find the molar extinction coefficients of a lot of the compounds at different states, in gas phase, liquid phase, and for a very different specific wavelength. Okay, so there are huge of information on the bibliography. You can find this data. And for example, here we have the molar extinction coefficient of hydrogen peroxide at different wavelengths. And we see that hydrogen peroxide at 254 nanometers, the absorption coefficient is not very high. It's about 18, 19. But if you lower the wavelength, if you increase the wavelength up to 295, 300, the molar extinction coefficient drops a lot. So the absorption capacity of this compound decreases a lot. That's why hydrogen peroxide process only works properly with UVC. Of course, if you have a new molecule and you don't know the molar extinction coefficient, it's very easy to obtain it in the lab. If you have a with the spectrophotometer, you can make solutions of different concentrations and obtain the molarization coefficient easily in the lab. What happens next when we irradiate the system with a specific radiation, with a specific wavelength? What happens in order to, if this compound absorbs energy, is that this absorption of energy generates an excitation of the molecule, normally based on the excitation of an electron in an upper energy state, and this generation of an excited molecule provokes an unstable situation that or has an excess of energy, which renders more probably the or the conversion of this excited molecule into products. So what can happen when the radiation is absorbed and we have these excited states? Here I summarize it in a very simple way, but basically there are different processes that can take place in the system. Some are, let's say, photophysical processes where the excited molecule returns to its ground state by different processes that they were already explained in the previous talk, that, for example, can generate heat or radiation or transition into different excitation states within the same molecule and produce, let's say, photophysical changes in the molecule. And it's important to remark that photochemical reaction is just one of a multiple pathways for this excited molecule to render products. There are very different type of routes on the loose of the excitation state of a molecule. Next, important topic to review, to take into account. One photon can only excite one molecule and can only render photochemical reaction on one molecule, and this is important. But there are a lot of processes that compete, or can be a lot of processes to compete on the excitation of this molecule. So there is an important parameter that relates the probability to undergo a photochemical reaction, and this is the quantum yield. So the definition of the quantum yield is the total of moles of a compound that is transformed, once this compound has absorbed energy, divided by the total of moles of photons absorbed by the system. Okay. This definition can be extended in continuous processes when we work in continuous, and then we have the number of molecules that react per unit of time, and the ratio with the number of photons absorbed per unit of time. And this quantum yield is very important because we can have a molecule with a very high molarization coefficient, with a very high absorbance coefficient, but with a very low quantum yield. And then you will see a low performance of the chemical changes in this molecule. And we also can have the opposite situation. We can have a molecule with a low molarization coefficient, but then a very high quantum yield. So the performance of the reaction depends on both, on the capacity of the absorbance of this energy and also on the capacity of this absorbed energy transform it into chemical reactions. So this is defined by the quantum yield. From here, the basic review of fundamentals in photochemistry about photochemical reactions. Okay, there are many different types of reaction pathways for these excited molecules. And here you have some classifications, basically dissociation, rearrangement, abstraction, substitution, addition. Okay, and at the end of the talk, I will give you some bibliography where you can find a lot of information on photochemical reactions. And must say this type of reactions, extraction, substitution, addition, they are very important in photochemistry, in organic synthesis, in photobiology, in many disciplines. They are very important. And we are focused on the reactions that, or let's say the main reactions that can happen when we apply just radiation to a system. So we are focused on direct photolysis and indirect photolysis. Direct photolysis, when we talk about direct photolysis, we're talking about basically two main types of reactions. The homolytic bond cleavage, or homolysis, that is also called homolysis. And in this type of reactions, where the compound absorbs energy and it gets this excited state, what it happens is that the bond, the electron pair that is in a bond, is splitted evenly in the two parts. So the product of these homolytic reactions are radicals. The typical homolytic photoreaction is the split of hydrogen peroxide submitted to UVC radiation into hydroxyl radicals. You saw in the table that hydrogen peroxide has a low molar extinction coefficient, but on the other side has a very high quantum yield. It's almost 1. It means that, that the equilibrium between the two characteristics renders the hydrogen peroxide a quite interesting advanced oxidation process. Another type of reactor is reaction is the heterolytic bond cleavage, or what is called photoionization. Here, the bond is split unevenly, and what you generate is at least one ion. And this electron that is released must be quenched or what must be accepted by another compound in the system in order to render the photoionization. That is the moment we're talking about quenchers and about oxygen. When we talk about quenchers, you're talking about compounds, different compounds that can be found in the reactor media, that they are able to interact, basically is collisions with the excited molecule, and then produce other ways of deactivating this excited molecule. And the ways of deactivating, there are different type of ways: physical quenching, basically by collision and vibration, vibrational energy transfer, or electron transfer. These are alternative ways of the activation of excited molecules when we have another compounds in the media. And both in natural waters, in water treatment, one of the common compounds is oxygen. If oxygen is present in the system, it can be easily produced from the reactions previously explained, the radical pathway by generating the superoxide radical anion. The superoxide radical anion is a quite reactive species that can react as a reductor, disprotonation, deprotonation, nucleophilic substitution, different type of reactions. But what generates is a pathway for generating radicals in the media, other radicals rather than superoxide radicals, like hydroperoxide radicals, hydroxyl radicals. So it's a contribution of generating radicals in the media, what is called reactive oxygen species, or ROS. When we talk about ROS, we're talking about these radicals that they are generated because of these photochemical interactions. photolysis, or these reactions are important in water treatment. Well, it depends completely on the molecule. It depends on this absorption capacity, and it depends on the quantum yield at specific wavelength. So the lower the wavelength, the higher the probability to produce some chemical reactions. But generally speaking, photolysis is not a very effective treatment for removing pollutants from water. And the efficiency normally is very low. If we move up at higher wavelengths, for example, using sun radiation, the efficiency decreases a lot. So we could see that direct photolysis is maybe not a very good water treatment, only for disinfection or only for specific cases, but it's very important in nature, because normally in nature you have water, you have oxygen, and you have other compounds. And of course we have the pollutants we are releasing in the media. So we have all the ingredients for generating these reactive oxygen species, so generating radical reactions in the natural media. They should not be there, or at least not in that extension. So this is a very important topic, and there are a lot of photochemistry, photobiologists, and also a lot of people from medicine studying these natural reactions in media, because they have very important consequences. I'll show you later or some of them. Here are some examples. This is clothianidin is a pesticide that is included in the last reviewed list from the European Community about molecules of concern. If you check the spectrum absorption of the molecule, it has a maximum at UVC region, and it decreases a lot at UVB region, but it still has some absorption in the UVB region. When you checked what happens under light radiation, we can see that with a not very high efficiency, but you have some degradation of the molecule. If you perform the same experiments without oxygen, normally by bubbling nitrogen in the media or using radical scavengers, you can see that there are almost no changes in the kinetics of the degradation of the clothianidin, so we can say this molecule is removed directly because of the absorption of light and the split of the molecule into byproducts. And here we have another different case. The chlorbos is another pesticide, also very toxic in all the lists. If you check the spectrum absorption, you would see that there is no almost absorption in the UV region, but if you amplify this region, you can see a little absorption in the UVB. So when you submit a solution of the chlorbos with sun radiation, you can see, again, a not very effective, with not a very effective kinetics, but you can see a degradation of about 30% of the initial pesticide in about 6 hours, only because of the effect of light, or at least it looks like only like the effect of light. If you removed, and this removal changes with pH. If you remove oxygen from the media, or if you use scavengers, like sodium azide, that is a very good, or terbutanol, they are very good scavengers, selective, well, almost selective scavengers for radicals, you can see that the removal decreases dramatically. So in this process, we have this implication of oxygen, probably because of the photoionization of the compound, because of the sun radiation, even though the absorption is very low. But you still have absorption, and this is enough for initiating radical reactions. You are generating radicals that can react with the promoter of the radicals, but if you have other compounds or you have natural compounds in the media, you can have these side reactions because of ROS, because of reaction of oxygen species. I also want to talk about indirect photolysis, what is called photosensitization. And this process happens when it is not an electron what is transferred to the quencher or to the other substance in the media, but is energy what is transferred. In this case, from the excited molecule to a second, to another compound. In this case, when the energy is transferred to oxygen, dissolved oxygen, you generate singlet oxygen. And this singlet oxygen, again, is an oxidant. It can promote different type of oxidant reactions, but it's also a promoter of reactive oxygen species. So what you have with this photosensitizing process is the generation of radicals in the media that, of course, it can be used in the proper way and to produce controlled radical reactions, but if it happens in the natural media, you can have negative effects on that. Photosensitizing reactions, there are people working on that. Still, the efficiency is low. And of course, you must add some compounds in the water. I didn't say anything about that, but sorry. But normally they are compounds with a chromophore moiety or that they normally absorbs in the visible region. For example, chlorophyll is a very good photosensitizer, but there are many others, like Rosbengals, chitosan, and many other compounds that with a lot of investigations, specifically in medicine and biology, they are found that many compounds, or anthropogenic compounds, have this photosensitizing capacity. And as I told you, it can be good or it can be bad. When it's done in a controlled media for removal of pollutants, as I told you, there are people working on that. Still, the efficiency is low, and you are adding a strange compound into the water. So, well, there are people working on supporting this material in a heterogeneous support. I mean, they are working on this topic, although still the efficiency is low. But again, these photosensitizing reactions are important in natural media, especially for those contaminants that are released to the environment because of the anthropogenic activities. Because, as I told you, every day many other compounds are being identified as photosensitizers. And for example, one typical photosensitizers are some sunscreens based on benzophenones and similar compounds that have been demonstrated that generates photosensitizing reactions with sunlight. If this sunscreen is on the screen, is on the skin, it can generate, let's say, medical problems, maybe cancerogenic symptoms. And many of them have been banned in different countries around the world. This is a photo from an announcement in Hawaii. Many of these photosensitizers that we're using in sunscreens, and also titanium dioxide, I think, they are forbidden because they are demonstrated that they generate the photo-bleaching of corals. Is it corals? Oh. So they're generating reactive oxygen species in water, in seawater, and in natural waters, and they have, of course, consequences. And one is the photo-bleaching of corals. So this is an important topic, and recently, in the last years, there are many works on dealing on the capacity of natural organic matter and effluent organic matter as a photosensitizers. We have to deal with organic matter when we want to remove contaminants in real waters. So it has been demonstrated that NOM and MEFOM can work as photosensitizers and producing other photochemical reactions, so they can work as ROS promoter, and at the same time, these radicals, part of these radicals, are quenched or are scavenged by the NOM. So sometimes you can see that the presence of NOM promotes the radical reactions and the degradation of a compound, and sometimes it decreases. And here, for example, this is with the chloropause, the picture I showed you before. With 2 ppms of humic acids, the degradation increase, because you have the photoionization and the generation of radicals from the activation of the dichloropause, but also because of the activation of natural organic matter. So you have both effects. When you increase the water content, or in wastewater, that is the case in this graph here, then normally the inhibition effect is higher than the promoting effect. And finally, just to conclude, to remember that there's also existing what is called vacuum UV photolysis, that is produced with vacuum UV lamps that are able to produce radiation below 190 nanometers. In this case, you have the split of a molecule of water into radicals in different pathways, and then the subsequent generation of other radicals that participate in almost all advanced oxidation processes. Here I invite you to obtain in bibliography the molar extinction coefficient of water at this wavelength. You will see that the penetration that is so high that the penetration depth is very low, which means that the reactant zone is very, very little and very close to the lamp, and this is a problem in water treatment. Maybe not so high in gas, but in water treatment it is very important. Okay, I finished with that. I wanted to give you some general bibliography. The first one and the last one, they are like textbooks on photochemistry, very complete with a lot of information. This is an interesting paper that is important in order to use, let's say, like official vocabulary when you work in photochemistry, because there is a lot of, let's say, misunderstanding on nomenclature, and this is very good. And I include this paper here, that is a review about how to detect, if you want to know better what is happening in your system. They explain a lot of methods, direct and indirect methods, for ROS detection in aqueous system. So I hope that will help you to amplify the knowledge of this talk. Thank you very much.